Nice to see you after lunch. So some further arguments in equidistributions will be discussed by Jon Chaika.
Okay, thanks everybody. So my plan for, I've got 5 more lectures. Yes, and my plan for these 5 lectures, all but one of them I'm going to do the Hopf argument, which is pretty awesome, so I'm excited about that, following an argument of Martin Babayot. My other 4 lectures are going to be a little bit of an absurdity. I'm going to give complicated proofs of a theorem that has a much, much simpler proof. In fact, I basically did it in 10 minutes in my last class on Wednesday. And why am I doing this? Because it actually gives very good proofs of hard theorems in other contexts. And in this context, everything is much more straightforward, so these 3 different ideas I think can be sort of crystallized in sort of a nice fashion. These 3 arguments are due to Yves Codene, Marina Ratner / Howard Masur, and Dani. They work very nicely in settings where you have a map of a space and you have a maximally expanded foliation or flow, and you have non-expansion in all of the other directions, and you're averaging with respect to over the directions you're expanding in. Okay, and we'll just present it in a very, very simple situation. Okay, so what we're going to do is we're going to prove the ergodicity of certain straight line flows on the torus, and in fact, unique ergodicity, that there's only one ergodic measure. And twice we're only going to do it for particular flows, for flows in particular directions, and once we'll do it for all irrational directions to kind of highlight some of the differences between the arguments. Okay, and so the first argument we're going to present is by Yves Codene. I should mention that on my notes for this course, I have an attachment where I've done a presentation of it, for a video of it for SL2R mod compact lattice, which is very much the setting that Davida has been talking about. So if you want to see the proof in that detail, and I think it'll also help if you want to see sort of how the other arguments would generalize. Okay, any questions on this? Great, okay, so let's get started. Okay, so all of my arguments are going to be about the interplay of this flow, and in particular for very special choices of V, of my vector V, with the following matrix. 2, 1, 1, 1. This is also a very nice map of R2 mod Z2 to itself, and it preserves a big measure. Okay, but let's say a little bit more about what we can say about this. Oh, I need to tell you what this is doing. So it takes, so 2, 1, 1, 1 has its normal linear action on R2, okay? That action preserves the integer lattice, so it descends to this quotient group, R2 mod Z2, which is just homeomorphic to the 2 torus. Everybody happy about that? And that's the action that I take here. Any questions on this? Great. Okay. Now the next thing I want to do is I want to discuss some very important data associated with the matrix, which is its eigenvalues and eigenvectors. Okay, so the eigenvectors of this matrix are 1 plus the square root of 5 over 2, 1, and 1 minus 1 minus the square root of 5 over 2. And these are orthogonal to each other, but that's not surprising because this is a symmetric matrix. Okay? And their corresponding eigenvalues are 3 plus the square root of 5 over 2, and its inverse, which is 3 minus the square root of 5 over 2. Okay? Nothing all that surprising. And so what does this mean? And I'm very sorry to be pedantic and be presenting this, but we're going to see this sort of all over the time, and so it's good just to do it out once, that this is equal to 3 plus the square root of 5 over 2. So that's a number, times 1 plus the square root of 5 over 2 and 1. Moreover, I can put a k here. And this is true for both positive and negative integers k. So let's write k. So this number is bigger than 1. So if I apply k to this, k positive, this is going to be a big number. But it's bigger than 1, so if I apply k negative, this is going to be a small number. Okay, so this direction expands in the forward direction and contracts in the backwards direction, and vice versa for the other vector, 1 minus 1 minus the square root of 5 over 2, and that's equal to 3 minus the square root of 5 over 2, k times 1 minus 1 minus the square root of 5 over 2. All right, everybody happy at this point? Somewhere between happy and bored? Okay, so what's the theorem I want to prove? The flow in direction if v is equal to 1 plus the square root of 5 over 2, 1, then f to the t of v has only one invariant measure. Lebesgue Let's talk through this briefly. So the content of the argument I'm presenting today is that there's only one invariant measure. It is not hard to see that Lebesgue is an invariant measure of this. Indeed, Lebesgue measure is invariant under isometries. This is an isometry upstairs, so Lebesgue descends to be an invariant measure downstairs. So if there's only one invariant measure and I know one invariant measure, I know what the one invariant measure is. Everybody happy about this? And if you remember from last week, I think it was my first lecture, I talked about the phenomenon of unique ergodicity, and that this gives you not only convergence of the Birkhoff averages for every point, but it gives you uniform convergence of these with respect to continuous functions. Okay? And so this is sort of a nice kind of result that's about uniform convergence. And in fact, Davide has done a fair bit in his lecture to talk about that in this special, in many cases, you can actually then ask questions about the rate, but that will play no role in my next 5 talks, the rate. Okay. All right, let's get started.
Can you clear the notation at the very beginning? It's FV, the theorem. It's FV equal the vector. What's it if the thing before F?
If.
Oh, thank you very much. If V is equal to this particular vector, thank you very much. Great. Thanks for the question. Any other questions? Okay, so the proof is based on the following sort of averaging operator or shifted averaging operator. Okay, so that's some pretentious words, but let me just define what this is. So let G be a one-Lipschitz function. I like working with one-Lipschitz functions. They're a rich enough family, but they make estimates very easy. So they're a convenient place to work. So what do I mean by they're a rich enough family? Their span, that's the Lipschitz functions, is dense, for example, say in L2 with L2 norm, or in continuous functions with supremum norm.
Sorry, what does it mean 1 before Lipschitz?
It just means that G of x minus G of y is less than or equal to their distance.
I see.
Okay. The Lipschitz constant is 1. Thank you. Okay, so I need to make a definition. I'm going to suppress the role of G in this definition just for notational convenience. some point a little later in this argument, I'm going to let the g vary, but hopefully that'll be clear what I mean when I do this. Okay? So it's going to depend on v, and it's going to be phi k of x will be equal to the integral from 0 to 1 of g of a to the k of f of t of x. Yeah, let's call it p dt. So what am I going to do? I'm going to take a segment, a flow segment of length 1, and I'm just going to average my function around that. But that's not quite right. I'm going to multiply that result by the action of this matrix A. Everybody okay with this? And as an aside, let's make the observation. Please tell me if this chalk color does not show up. This is the same thing as...
So x is the same as p.
X is the same as p. Thank you. As 3 plus the square root of 5 over 2 inverse times the integral from 0 to 3 plus the square root of 5 over 2. Inverse I meant to the minus k. This is to the k of g of f to the t of a to the k of p. Okay.
But the argument on the left-hand side should be p, right? Not like...
Thank you very much. Thank you. Thank you. I was stubborn in my typos, so thank you for your constant correction, for your helpful corrections. Okay, so this is very much like the statement about the conjugacy of the horocycle flow. Let's take a moment to sort of pause, because that's secretly the context I have in mind here. But I don't need to work with Lie algebras, I don't need to work with careful coordinates, because the space I've chosen is incredibly nice. Okay, so what am I doing? I'm doing some kind of a flow. Think of this being as an analogy with a horocycle flow. And I'm looking at the effect of another action on it. Think about that as the geodesic flow. And the statement is that that's the same thing of a much longer piece of that action, of that flow, if I act first by my action. Okay? So sometimes there's a buzzword used in this setting called renormalization dynamics. And what's the idea? The idea is that my action of A, either forward or backwards, lets me change very long orbits into shorter orbits or vice versa. So it renormalizes my scale. I won't mention that too much, but just to kind of give some context. Okay, and so what's the sort of key of this argument is the following beautiful proposition, to my mind at least, of course. Probably it's a little bit like a Rorschach test, what you think is the meat of a proof and what you think are sort of the details of the proof. But to me, the following thing is the meat of the proof, which is that the set of operators phi sub k, for k in the natural numbers, not in the integers, is an equicontinuous family. Okay, so what do I mean by this? I mean that for all epsilon bigger than 0, there exists a delta greater than 0, so that for all p in my torus and k in the natural numbers, if the distance from p to q is less than delta, then the difference of phi k of p and phi k of q is less than epsilon. So uniform continuity would be not worrying about the k and that this holds. I've got a family of functions, and I want the modulus of uniform continuity to be uniform over all of them. Everybody happy about this? Now, why do I care about this? Because ergodicity is very much a procedure about limits, okay? And Arzela Ascoli gives you that equicontinuous families of functions have limits, okay? So this is sort of the key point of the argument, and then we're going to study the limit of this. We're going to show that it's ft invariant. And under the assumption that we have a dense orbit, we will then obtain that it's a constant function. That's how the proof goes. Okay, so this is kind of a key step. Any questions at this point?
The result, the proposition is for any f or for f.
There is a function that's fixed. Maybe I'm missing what you're saying. We fixed a function g. From that, we've defined phi sub k. This is now a countable family of functions, and I'm claiming it's an equicontinuous family.
F, capital F, is
Yeah,
For every
always
part.
fixed. No, not for NF.
For this particular
particular.
fund, this is all fixed.
okay.
Okay, great. Yeah. Okay, any other questions? Thanks for the question. Any other questions? Great, let's proceed. Okay, so for convenience, so I'm free to choose my metric, right? And so for ease, we choose the L1 metric. Given by coordinates, linearly independent coordinates, 1 plus the square root of 5 over 2, 1, comma, 1 minus 1 minus the square root of 5 over 2. Basically, this avoids a bunch of factors of square root of 2 floating around. Okay, so this is just kind of for ease. Is it clear what I mean by the L1 metric given by this choice of coordinates? Great, okay.
Sorry,
Yeah, sure thing.
No. So what do you mean?
Yeah, thanks.
So you take these two guys as the base? And
Yeah, and so you represent things in R2 in coordinates with this.
in R2, not on the torus.
Yes, and then it descends to give you a metric on the torus.
It gives you a metric on the torus.
Just by considering the minimal length path on the torus between 2 points, and then you lift that path back up to R2, and it gives you a metric there.
I see.
Great. Okay. Thanks. Thank you for the question. Okay, so what are we going to do? We will show. So delta is pretty complicated, but here delta is going to be very simple. It's going to be epsilon over 3. So let x and y be less than epsilon over 3. Okay, and k be in the natural numbers. And we want to show is less than epsilon. Everybody happy about that? And maybe I need to close my absolute values. Yeah. Great. All right, so what I'm going to do is, so there exists A, comma B, and the reals, and in fact, not too big, so that A plus B is less than epsilon over 3, and Y, let's make sure I'm doing this on the correct side, yes, Y is equal to X plus A times 1 plus the square root of 5 over 2, 1, plus B times 1 minus 1 minus the square root of 5 over 2. That's what it means for their distance to be less than epsilon over 3. And if epsilon is small, say less than a quarter, these A and B will be unique that can do this. All right, so now what I want to do is so I'm going to be using the fact that the guy I'm plugging in here is 1 Lipschitz. So what I really want to do is be estimating the distance between a to the k of the f of t of these points and a to the k of f to the s of the other point. Notice I picked different letters for t and s. All right. So, okay, so I want to simplify. So one of these guys is just going to be x, that's sort of my base for which to consider. And I want to look at what a to the k of ft of y is going to be equal to. Maybe, yeah, I'll leave in the v's. Ft of y, and that's going to be equal to, well, it's going to be a to the k of ft of x plus a to the k of a 1 plus the square root of 5 over 2, 1 plus b times 1 minus the square root of 5 over 2. Okay. I'm acting by translations, and I have the distributive property of the action of a matrix plus a vector. And so I can distribute the action of A to the flow part, ft of x, and to this part. Everybody okay with that? Should I do another line of description, or is everyone happy with what I wrote? Who's with me right now? Oh, fantastic. But not everybody, so maybe I'll do an intermediate remark, which is that if I flow x and I translate, that's the same thing as flowing the translate of x. And that's just because different translates commute. I can add this first, and then I can do my flow, which is just a translation by a particular amount for fixed t. Or I can flow first and then translate. And two translations commute, so it doesn't matter which order I do it in. Okay? So I first pull out this part from my flow, and then I have my flow, which is just a translate of x multiplied by a matrix, and the translation vector multiplied by a matrix, and of course by the distributive property, or by linearity, that's the same thing as the action of the matrix on both of those things. Who's with me now? Great. I think that's pretty close to 100%. Okay, so now we're just going to take advantage of what we have, and so we're going to leave this term the same, and now let's look at what this term is going to be. That's going to be a times 3 plus the square root of 5 over 2 to the k. So this is some horribly enormous number, which is kind of scary. And now I get some tiny number, which is great. So this is going to be 3 minus the square root of 5 over 2 to the k times 1 minus the square root of 5 over 2. Okay? And then this piece is just the same as before, a to the k of f to the t of x. Okay, so the only complicated thing I've done is I've done here. Okay? And so I've got good news and I've got bad news. I want to plug this into a one Lipschitz function, and I want to compare it to what happens when I plug in g of a to the k, f to the t of v of x. Everybody happy about that? This part isn't going to matter at all, because it's negligible, it's tiny, and my function's one Lipschitz. Okay? This part's going to be horrible. It's going to be completely changing everything that's going on. Okay? And that's where the sort of great cleverness comes in. The fact is that because I'm averaging, by changing the base point, I'm going to get a lot of cancellation between this. Okay? So if you remembered when I talked through this, I used different exponents in the flow, different times in the flow, and there's going to be a shift of time in the flow that will relate them. And it won't be a mysterious number, it'll be this A. Okay? Oh, but of course that was just me blathering, so now let's try and actually do some mathematics. Okay, observe. Observe. A to the k of ft of p, indeed, is just equal to p plus 3 plus the square root of 5 over 2 to the k of 1 plus the square root of 5 over 2, 1. Okay, so that's what that is. That's just, plugging in what's happening. It's very much the same as this step here. Okay. And so, a to the k of f to the t of y. Will people see if I write on this line? I can't tell if it's blocked by this. People will see. Okay, I won't write any lower than that. So that's going to be equal to a to the k of f of t plus a of x plus b times 3 minus the square root of 5 over 2 to the k of 1 minus 1 minus the square root.
So you lost t probably
Over 2.
in the first line.
I don't, so are you saying I made a mistake here?
No. Here also, but okay. So you flow by the flow until the time t. So t is missing on the right hand side. Am I right?
Where, I'm sorry, there's a lot of lines, so.
Top right corner.
Top right corner, yes, you're 100% right, I'm missing T on the right hand side. Sorry, there were just too many lines, I didn't, too many places. Thank you.
And the same in the lower line, of course.
This line? I think that T is here.
No, sorry.
No, thank you very much for this.
You're right,
This is
sorry.
great. Okay, so what's going on here? If you let this T be equal to this A, okay, that's going to give you this missing term right here. Okay, and so what I've done is I've taken this term here, okay, and I've put it here. Okay? And by the action of A, that's what I get. Is everybody happy about this? Okay, now we just do some basic tricks from maybe calculus even. Is everyone okay if I erase? So now I'm in perfect position to apply phi to the k to both of these. Okay. So now phi to the k, or I'm sorry, phi sub k of x minus phi sub k of y in absolute value, this is going to be equal to the integral from a to 1 of g of a to the k of f to the t of x plus, minus g of a to the k of f to the t of x plus b times 3 minus the square root of 5 over 2 times k times 1 and then 1 minus 1 minus 1 minus the square root of 5 over 2. Okay. There's going to be 2 more terms, but let's talk through what's going on in this term. I'm starting my integral at a, so I'm looking at parameters in my first variable, so parameters of x, which start at a. And I do a change of variables here where s plus a goes to s. Okay? So I start this parameter here when t would have been 0. Okay? And that gives you an a. Everybody okay with that? All right, and that now leaves me with 2 remaining terms. I need to put absolute values around this. Now I have 2 remaining terms. Now I have the integral from 0 to a of g of a to the k of f to the t of x. And then I've got my last term, which is, I guess you can put minus the integral from 1 minus a to 1 of g of a to the k of f to the t of, let's just put this as y to kind of clarify what variables in what place. All right. And I'm integrating all of these with respect to dt, so hopefully it's okay that I'm suppressing the dt. Okay, is everyone happy with where this term came from, from a change of variables in the f to the t of y? Yeah.
I guess I have to come back.
Definitely.
Sorry, can I?
Yeah.
So I think that everywhere here you should add t. So this is probably not important, but nevertheless you flow here by time t. And
I don't think so, because these are just translations, right? So in vectors, this is going to be tv plus y plus tv plus this
it
vector.
doesn't matter
and it
here.
can be-
Okay, sorry.
No. You might be thinking about the horror cycle situation where you have to move coordinates, but here life is good. Okay, thanks. Any other questions about that? Okay, great. So I now want to estimate this. And so this is going to be, so it's an element of the torus here, an element of the torus here, and a small perturbation here. So because I'm one Lipschitz, this is going to be less than or equal to b times 3 minus the square root of 5 over 2 to the k. So something that decays exponentially quickly in k. And I'm integrating over something of size at most 1. So, or really 1 minus a, but I'll just overestimate and say that this is 1. So that's the estimate of this entire term here. Okay. And this term here, I can let it be 2a times the diameter in my metric of the torus. Everybody happy about this? Great. Okay, and so I've proved my result. Okay, because A's size was controlled at the very beginning by the closeness I chose, right? The closeness of these points better play a role, and it plays a role right here. So any questions on the proof? Let me go through what the ideas are of the proof. So there's sort of two basic ideas. One is that you get contraction coming from A in a lot of different directions, in some directions. And for those, because my function's one Lipschitz, everything will take care of itself really wonderfully. Now I've got expansion going in another direction, which is really scary. That looked really bad. And so if there's one takeaway of this argument, expansion can be taken care of by averaging it out. Because the expansion is in the direction of the dynamics, you can take care of it as by averaging out along the dynamics. Okay. All right, so now we're prepared to wrap up the proof. Yeah, I guess I'll erase this. So the whole point of what we were talking about is the fact that we're going to get limits. So before we discuss that, let's just talk about what the properties these limits will have. So we have the following lemma, which will be a consequence of the von Neumann ergodic theorem, which is that any limit, say L2 limit of any L2 limit of the phi sub k is f p sub v invariant. Okay. All right. So let's say a word about why this is. So let's recall what phi of k is. So phi sub k. K of x, it's going to be equal to 3 plus the square root of 5 over 2 to the minus k of the integral from 0 to 3 plus the square root of 5 over 2 to the k of g of f to the t of a to the k of x. Okay? So let's just make a quick remark that if there wasn't an a to the k here, the von Neumann ergodic theorem would tell me that this would be converging to projection onto the ft invariant functions. But there is one, so let's take care of that. So let P be equal to projection orthogonal onto f to the t v invariant functions. Okay. And by the von Neumann ergodic theorem, the norm of P of G minus phi sub k composed with a to the minus k goes to 0. Okay, so what have I done? I've sort of remembered that I've got a function g around here, and this is going to be converging to p of that function g. That's sort of my target. But I need to undo this a to the k here, so I'm just undoing that a to the k. Everybody okay with that? All right. But now a is measure preserving. So just as a number, this is the same thing as p a to the k of g minus phi sub k. Okay. All right. And this guy's ft invariant, so this is going to an ft invariant function, so any limit has to be ft invariant. Because a to the k sends ft leaves to ft leaves. A to the k preserves ft invariant sets. A set of f to the t invariant functions. Let me make a moment to make a remark. So this argument is going to be very special and everything is going to work out really well. There's a lot of ways to view this as upgrading topological information to measure theoretical, upgrading ergodicity to unique ergodicity. When you're trying to upgrade ergodicity and you're moving your base point, which is what's going on here, usually that's sort of a disastrous thing to do. There are some special arguments where it works out. This is one of them. But in general, when you're moving your base point, you can be creating a lot of problems for yourself. Okay, so sometimes things are so slick you miss sort of moments where you should be cautious. And when you're moving your base point, that's a moment where you should be cautious. Okay. All right, so now we're basically done. Okay. So what we've shown at this point is that, so I want to state two corollaries. So corollary one, to prove the ergodicity, the FT ergodicity it suffices to show that phi sub k, any limit point, any limit of phi sub k is a constant function. Okay, and what's the idea of the proof? The von Neumann ergodic theorem tells you that this is projection onto the invariant functions. And you're ergodic if and only if those are the constant functions. Okay? Now, G was an arbitrary one Lipschitz function. So if I get this for a one Lipschitz function, for G I get this for any one Lipschitz function. Now, by the linearity of pretty much everything in sight, I get this for the span of my one Lipschitz functions. Okay? And by L2 boundedness of everything in sight, I get this for the L2 closure. Now the span of the one Lipschitz functions is the Lipschitz functions, and they're dense in L2. So knowing that all of those project to just the constant functions means that all of my invariant functions are the constant functions. Everybody okay with that? Does anybody want me to explain a little bit more about that, or maybe write the words I just said? Okay, great. Oh wait, then there's one more corollary, which is corollary to prove the only invariant measure of f to the t is the area, is lambda. It suffices to show any limit of phi to the k is constant. So not only do we have ergodicity, which seems the most immediate from studying what's going on with the von Neumann ergodic theorem, but also you get unique ergodicity, that this is the only invariant measure. Okay.
Sorry, John.
Yes, please. Oh yeah, please.
Did we already prove ergodicity or?
No, we haven't. We've proved that it's enough to show ergodicity if any limit is constant.
Ah, okay.
And now I'm saying,
okay.
and now I'm saying that not only that, you actually get unique ergodicity. You get that the only invariant measure. And let me just say a few words of why this is true. So if I have two different ergodic measures, if mu and nu are two different ft ergodic measures, there exists h Lipschitz, say one Lipschitz, so that the integral of h d mu does not equal the integral of h d mu. Is everybody happy about this? Okay. Now, by the Birkhoff ergodic theorem, just thinking of h as being a as just being an L1 function. If you're one Lipschitz, you're L infinity, and this is probability measure. Your L1, there exists P and Q, let's say P sub mu and P sub nu, so that the integral of 0 to L of h of f to the t of P sub mu dt, 1 over L, converges to the integral of h d mu. Everybody happy about that? And then similarly with nu's for P sub nu, but I'll just save time by not writing that. Okay. Now what this tells me is it tells me that phi sub k of a to the minus k of P sub mu converges to the integral of h d mu. Everybody happy about that? Okay, now these have my torus is a compact space. There's a subsequential limit, and I'm equicontinuous. So any subsequential limit point will also have the property that these phi sub k converge to the integral of f d mu. Okay, also true. For x equal to the subsequential limit. Okay. And of course, there was nothing special about the subscript mu. The same thing would happen with the subscript nu, and so you couldn't be going to a constant function. Everybody okay with that?
Sorry.
So the point is that by equicontinuity, if you have different points whose integrals, whose Birkhoff averages are different, you'll have to have that the phi sub k's have this property as well.
Okay, but on the I can't see. I can't see the final step. Sorry.
Okay.
So could you repeat again?
Yeah, so let's assume that I have a subsequence on which this converges to a constant function, and let's get a contradiction.
Yeah.
Passing to a further subsequence, I can get that these p sub mu's are converging to an actual limit point, say x. Okay?
I see.
But the value at these points that are nearby isn't that far because it's equicontinuous.
Okay. Okay.
Did that make sense?
Yeah.
Great, thanks. Any other questions on this? Okay, now we're basically done. So proof of theorem. Proof of theorem. By Arzela Scoli. Since the phi k are equicontinuous, there exists a subsequential limit. Sup norm limit. Let's call it, I don't know, psi. Okay, that's what equicontinuity says. Everybody happy about that fact? Yes? Oh, you're raising your hand for happiness. Awesome. Okay, there exists a subsequential limit, okay? This is an L2 limit as well. Is an L2 limit as well. And so is f to the t invariant. Okay. The t invariant right there. Now there exists a dense ft orbit. So phi is a continuous function constant on a dense set. And so is constant. Okay, that's the argument. Any questions at this point?
Okay, so you use the fact that this guy is continuous, is invariant, and the flow is minimal.
Yep, or just that there's a single dense orbit.
A single dense orbit, okay.
So maybe I can make some remarks motivated by this thing you just said. Okay, so this generalizes very nicely into SL2R mod compact quotients. Okay, generalizes very well. SL2R mod compact quotients. Co-compact lattice. But it also generalizes to SL2Z. SL2R mod SL2Z. So pretty much every step goes through absolutely wonderful, except there's one thing that shows up, which is a couple of times in our proof, we've realized that we're moving our base point around, okay? So if I want to understand what's happening to the long horocycle orbits, and horocycle flow. If I want to understand what's happening to a long horocycle orbit, I need to pull back under the renormalization dynamics, under the geodesic flow in this example. And so what I can't have happen is I can't have that leaving my space. Can't have that leaving my world. So you only get that the orbits equidistribute if under the pre-image of the geodesic flow, they don't diverge. Meaning leave every compact set, never to return. Okay? And that's actually what happens in SL2R mod SL2Z, is that you have every orbit equidistributes to the Haar measure, except if under the pullback by the geodesic flow, they leave every compact set, never to return. Okay? So this change of base point really does show its head. Okay? Okay, I think this is a good place to stop.
Question, remarks? Asking for more explanation?
Let me also mention that there's nothing special about one dimension in this. What's important is that you're averaging over all of the directions of that are expanded. Okay? And you can even have additional directions that are not contracted but are central. And you do have this.
You say that it works for higher rank actions, or?
Horospherical subgroups.
I see.
And, yeah.
That's it. Okay, thanks again. 20 minutes break.
I know.